Imagine you're driving a car at 100 kilometers per hour. Now imagine another car passes you going 120. Easy to picture, right? You see the faster car gradually pull ahead and disappear into the distance. But now, replace those cars with beams of light. If one beam of light moves next to another, can it overtake it? Can one ray of sunlight sneak ahead of another and win the race? Intuitively, it feels like it should be possible. If we can add speeds in everyday life, why not with light? Here's the twist. No matter how fast you're going, even if you're moving at nearly the speed of light, a beam of light will still pass you at the exact same speed it always does. About 300,000 kilometers per second, no matter what. And that's weird because that's not how anything else in the universe behaves. Throw a ball on a moving train and someone standing still will see it move faster than someone sitting on the train. But shine a flashlight on a train and everyone, on board or off, measures the beam moving at the same speed. So how is that even possible? Why doesn't light obey the common sense rules of speed addition? What's so special about it that makes it untouchable? To answer that, we need to zoom out, way out, and shift our perspective, not just on speed, but on space and time themselves. You see, the universe has a speed limit, not like a polite suggestion, but a hard, unbreakable law. That limit is the speed of light in a vacuum. And it's not just a rule about light, it's a rule about how space and time work at the deepest level. The moment you try to imagine something going faster than light, the math of reality starts to break. Events can happen before their causes. Distances become undefined. Clocks go haywire. It's like asking your GPS to show you a shortcut that arrives before you even leave. The universe simply doesn't allow it. But why not? Let's slow down and build this puzzle from the ground up. Because once you understand why light can't be overtaken, not even by itself, you unlock something profound. You begin to see space and time not as a stage where things happen, but as active players. And you realize, to protect the cosmic speed limit, the universe bends reality itself. So buckle up. We're about to enter a world where time stretches, distances warp, and the speed of light becomes the glue that holds the rules of physics together. And it all starts with one deceptively simple question. What even is speed? Let's break this down. What do we actually mean by speed? At its core, speed is just distance divided by time. How far something moves and how long it takes to get there. That sounds simple enough until you start asking, what if space itself stretches? What if time ticks differently depending on how fast you're moving? That's when things get weird. And welcome to the world of Einstein. Before Einstein, people thought of space and time as fixed, like a grid or a stage on which the universe plays out. You move through it, but the stage doesn't change. But Einstein shattered that view. He proposed something radical. Space and time are not separate things. They're part of a single entity called space-time. And the speed of light isn't just a fast number. It's a fundamental feature of this space-time fabric. Here's where our key analogy comes in. Imagine space-time like a stretchy sheet of rubber. Every object, a car, a planet, even you, moves across this sheet. But there's a twist. The rubber doesn't let anything move faster than a set limit. If you try to push harder, it resists. The harder you try to go faster, the more the sheet pushes back by stretching time and compressing space. Now, light doesn't have mass. It doesn't need fuel. It's like a puck on the ice, gliding effortlessly. And the rubber sheet? It allows light to travel at the maximum possible speed, the speed of light. That's the fastest anything can move, not just because it's a limit of technology, but because it's baked into how the universe measures time and space. So what happens when you start speeding up, trying to chase that beam of light? Space-time itself adjusts. Your clock ticks slower. Distances shrink in the direction you're moving. The faster you go, the more extreme these effects become. And just as you feel like you're catching up, space-time pulls its trump card. It changes the way time and space behave for you to ensure that, from your point of view, the light still zips by at exactly the same speed. This isn't just a trick of measurement. It's not that we can't see the light moving faster. It's that it physically can't move faster, because any increase in speed would require bending space and time in impossible ways. In fact, trying to push a particle with mass to the speed of light would require infinite energy. And for anything with mass, like us, or our ships, or our dreams of warp drives, that makes light an unattainable ceiling. But here's the wildest part. Light doesn't experience time the way we do at all. From the photon's own point of view, if we can even call it that, no time passes as it travels. A photon emitted from the sun and absorbed in your eye billions of kilometers later experiences that entire journey as instant. Zero time, one event, beginning and end collapsed into one. So now think back to our original question, can one beam of light overtake another? The answer is no, not just because they move at the same speed, but because light doesn't exist in time the way we do. It doesn't have a before or after in the same sense, it just is. It's the fastest thing in the universe because it doesn't experience motion through time the way we do. Trying to make light move faster would be like asking a shadow to cast itself. The question unravels once you understand the nature of what you're dealing with. But we're not done yet. Because now that we've accepted that light defines the speed limit of the universe, the next question is, how does that limit shape everything else? What are the consequences of this cosmic speed cap for the way our reality unfolds? Because the answer might just blow your mind. Let's imagine a universe where you could go faster than light. You hop into your futuristic spaceship, fire up the engines, and zoom ahead of a photon. What happens next? Well, the universe would have a complete meltdown. Causality itself would start to unravel. Why? Because faster than light travel isn't just about speed. It messes with the very order of cause and effect. Here's a thought experiment. Suppose you send a message to a friend faster than light. In your frame of reference, it leaves your device at noon and arrives at their place at 11:59 a.m. It got there before you even pressed send. That's not just weird, it's a paradox. Now imagine your friend reads the message and decides not to respond. Suddenly, your message is never sent in the first place. This kind of loop, where the effect cancels the cause, breaks the rules that keep reality consistent. Einstein's theory of relativity doesn't just put a speed limit on how fast things can move. It protects the logic of the universe. It ensures that events unfold in a way that makes sense, that causes come before effects. The speed of light is the ultimate referee, making sure no information travels faster than what space and time allow. It's not about slowing us down. It's about keeping time itself from falling apart. But wait, don't particles in the universe sometimes move faster than light? It turns out, yes, kind of. There's something called Cherenkov radiation. It's a glow, often blue, seen in nuclear reactors. It happens when particles move through a medium, like water. Faster than light can move in that medium, not in a vacuum. Light slows down in materials, but those particles don't. So they briefly outpace the local light speed and produce a shockwave, like a sonic boom, but with light. Still, that's not faster than light in a vacuum. The cosmic speed limit remains untouched. And what about quantum entanglement? You may have heard that two entangled particles can communicate instantly, no matter how far apart they are. That sounds like faster than light messaging, right? Not quite. Yes, entangled particles have linked behaviors, but you can't use that link to transmit actual information. It's more like two coin flips that always match, but no one controls the outcome. There's no signal being sent, no way to cheat the light barrier. So everywhere we look, from particle physics to cosmic scale, the same rule holds. Nothing with mass or information can go faster than light. And even light itself, elegant and swift, never breaks the rule. It doesn't speed up, it doesn't slow down. It defines the limit. That brings us to a deeper realization. The speed of light isn't about light, it's about structure. It's the scaffolding of the universe, the constant against which all motion is measured, the speed that space-time was built to preserve. If you change that, even slightly, you don't just make photons go faster, you change everything. Chemistry, atoms, life, the universe as we know it wouldn't work. So when we say light can outrun itself, we're really saying that reality has boundaries, and those boundaries are the reason it makes sense at all. The reason we have laws of physics, the reason clocks tick, the reason cause leads to effect. In a way, light is less of a traveler and more of a rule book, the pulse that defines time and space for everything else. So now we understand why light can't outrun itself. It's not about speed in the traditional sense. It's about the framework of reality. Light defines the fastest way information can move. It's the ultimate speed not because of technical limitations, but because of how space and time are wired. In fact, the speed of light isn't just a number in physics textbooks. It's baked into the equations that describe everything, from the way your GPS works to how stars burn and black holes warp space. If the speed of light were even slightly different, atoms might not hold together, stars might never ignite, and life as we know it could be impossible. The cosmic speed limit is what lets the universe behave. Consistently, predictably, beautifully. Think of light as the stitching in the fabric of space-time. Try to pull that thread faster than it was designed to move and the whole thing unravels. That's why no matter how advanced our technology gets, we'll never build a ship that zooms past a laser beam. Because doing so wouldn't just break the rules, it would break the game board. But instead of being frustrated by this limit, we should be amazed by what it means. The fact that there is a universal speed limit tells us something profound. It tells us that reality has order, that time has meaning, that there are rules, and those rules make complexity, life, and intelligence possible. So, the next time you see sunlight dancing on the wall or a beam of a flashlight cutting through darkness, remember, you're witnessing something special. Not just fast, but fundamental. Light isn't just the fastest thing in the universe. It's the rhythm that time marches to, the ruler by which distance and duration are measured. It is in many ways the heartbeat of the cosmos. And if that made your curiosity light up, pun absolutely intended, then you're in the right place. Hit that like button, share this spark of insight with someone else, and subscribe to How It Actually Works. Because here, we don't just explain science, we unlock its secrets in a way that makes your world brighter.